It's really a pleasure to be here. Thanks for the introduction. This talk would be, divided into two parts. So there's going to be one part of this talk where I'm going to be talking about sequence modeling and machine learning techniques that deal with that we have applied to laboratory earthquakes. And then there's going to be a second part where I would be talking about machine learning techniques that we have not yet applied to earthquakes. So the first part is going to be, well, I'll tell you where we go. The second part is going to be about graph convolutional networks. And so I hope this would be inspiring some of you. So let's get started then with the first part. And I mean, I'll try to model time in a flexible way. So Chris tells me I've got roughly 1 hour, but I'm really, I don't need to, I've got a lot of material that I put together. So it's, I'm also happy to interact and to be interrupted, so feel free. So for the first part, I'm going to be talking about, say, sequence modeling, forecasting, lab quakes, some introduction, then forecasting models that I would focus on, and then show you what we have. This is based on work that is currently, say, under review at the EPSL journal, together with Chris, Laura Laurenti, and Elisa. Right, so let's get started with an introduction to deep neural networks for sequence modeling. So probably most of you are most familiar with this sort of deep neural networks. So deep neural networks that look like you have an input, which generally is an image. Then you have some processing, so a neural network there, something deep that has got a lot of layers, and then you got an output, which is a label. And for example, in the case of ImageNet, you want to say there is a steel drum within the image. So if you tell me there is a steel drum, then thumbs up, you get it right. In reality, very few, I mean, the majority of tasks in the world are not dealing with this sort of, say, vanilla one in, one out, but rather have got to do with input and outputs that are actually many. And so, for example, and so we got sequence tasks, which stand for example, for image captioning, meaning you take an image in and you want to describe it. And so you've got multiple words that need to be produced. Or you've got sentiment classification. So you've got a list of words, and then you want to tell whether this was something positive or negative, something that banks can use to understand whether they should invest into a share or not, based on Twitter. And then you got, say, many-to-many tasks. Well, or sorry, what to say? Another many-to-one task is you've got several video frames and you want to classify them. Then, and this is getting to, say, more interesting things, you've got many-to-many types of sequence modeling. And for example, this is about producing sequences of words out of sequences of words. For example, machine translation. So you read a sentence in Italian and you want to translate that into English. Clearly, say in I don't know, I guess you see my mouse. So in this video, basically you stock in what you've observed, and then you output your prediction. Or there are some tasks that are like many-to-many, and an example for that is, say, classifying a video while it happens. So what's the progress in an action so far, what kind of action that is, and so on. Okay, so well, which of these say sequence models fits best to forecasting? So any guesses?
It depends, Fabio. If you want several things, including magnitude, possibly location, and timing, well, it's many to many, right? Probably many to many. It could be one to many, but if you just want one aspect of forecasting, you might go many to one or one to one. What do you think?
Right. I agree. I mean, I think this is the most complete one, where basically you may predict the future, but in the meantime you keep observing. Yes, right. Um, I was more kind of say going to focus on this because say in the forecasting, one may also say, you know, um, you want to predict into the future, so you stop seeing what happens, but of course this can be seen as say many to many if you keep then forecasting and updating your forecast, and if at the same time you want to estimate certain features, and probably you need the two of them, right? And there is actually something that I'm going to be arguing today about, which is the fact that if we are able to forecast, then it's actually going to be useful to be able to establish this sort of link, which we call, which makes the prediction actually autoregressive, because this means that we will be predicting one step ahead in the future. Then we're going to be able to keep processing this and predicting again one step in the future, and then keep doing that. And there are a number of reasons why we like it. I'll touch upon some of them. But say somehow you can imagine this as a way to forecast at an indefinite point into the future, right? Keep forecasting, keep extrapolating your knowledge, the knowledge that you can get to. So before meeting with Elise and Chris, I have been mainly focusing on, and I'm still doing say research on these tasks. So people trajectory forecasting, meaning that I'm trying to predict where the people are going to go based on their previous positions. So we know where they've been, world coordinates, and we want to predict the future. And also we are predicting the joints of people. So we know how they have moved, and we want to predict how they will move. And this is really important to predict, for example, whether somebody is going to cross the road, but say sticking with more with what we effectively do. We have a collaboration with the University of Verona, and we're dealing with cobots, and so we're making it so that the robot stops well in time before the collision, and for that we use forecasting. But certainly here we want to contextualize this into the field of laboratory earthquakes. So we're considering the setup that probably every one of you is familiar with, which is the setup of the experiment of Chris. And we're talking about a controlled environment because we got control on many of the pretty much on most of the aspects of the experiment. So we got a predefined normal stress, we got a constant velocity loading, and then we simulate some instabilities. And and there are, say, a number of experiments that we have. In particular, we've considered 3 that differ because of periodic or aperiodic instabilities, seismic cycles, fast, slow, fast and slow, and because of the materials that are within the default gauge. So be that quartz or glass beads. Since it's a controlled environment, we can record the audio, but also we can record, say, the stress. So we can record the force within the ground that pushes. And now basically, we like to think about this in terms of, say, 3 sort of layers of knowledge. So the acoustic emission is what you can effectively observe also in natural earthquakes. Then there is some underlying, say, shear stress within the ground. And then finally, there's what potentially you may want to predict as your goal, which is, say, the time to failure, right? So how long before the next discharge of shear stress, the end of a discharge or the beginning of a discharge. So time to the start of failure or time to the end of failure. Right, in the submission that we currently have at EPSL, we have dealt with 2 aspects. So the first one is, say, how to go from the variance of acoustic emission to predict the stress at the same point in time. We call it a prediction. So here you really want to estimate how much it is the shear stress at that same period of time. So you read anything that has happened so far and you estimate the shear stress. I'm not going to talk about that. So instead, I'm going to be talking about forecasting. And I'm sorry for this slight, possibly, say, misleading terminology. So, of course, forecasting is also a prediction goal. But what I mean by forecasting is that it's going to be a delta in time. So we're going to be forecasting what happens in the next, say, 100 steps, in the next 10 seconds. Right, so there are 3 main experiments that we have considered. So the first one is one with a quartz fault gauge, and this is going to be about, and this is about periodic slow slip event. It is, of course, more regular, right? And potentially, as we may expect, easier to predict. Then there is one other experiment that we have considered, and this is one with glass beads. And here we got a semi-periodic slow slip event. And then finally, there is another experiment with quartz. And here we are alternating the slow and fast events. So let me be a little bit more, say, formal, I think, very little bit more on what we mean with autoregressive forecasting. Well, this is basically the definition of forecasting. You observe, say, from time t minus p, past, where p stands for past, right, up until time t. So you've got p plus 1 observations. And then you predict from t plus 1 into t plus n, which stands for the new steps into the future, and potentially beyond. We're going to be using this model, so which means that once we have predicted t plus 1 also becomes an input into the model, so that we can use anything from t minus p up until t plus 1 to predict t plus 2. And this autoregressive part is really what we believe is a good thing for a number of reasons. And I'll in the second part, I'll get again onto this. But currently what I want to tell you about is that this is self-supervised. I don't need anyone telling me what to label. And this is really important in machine learning. There is a lot of ambiguity whenever a person is involved in labeling. And in fact, labeling is ambiguous. So we have it all the time. So I'm dealing with action recognition, and it's always difficult to say when an action starts and when an action ends. And sometimes the actions are actually overlapping, right? And here, for example, if you look into this picture, potentially there are two failures, right? So which one do you want to predict, the smaller or the bigger, right? So it's this is an ambiguity which you can also observe in this sort of signal. And if you predict exactly the value of shear stress into the future steps, you don't have this sort of ambiguity. So this is really important. This makes a difference. And also, of course, of course, the model is best at what it has trained, but you can also just challenge it to predict more. And nothing stops you from saying, okay, let's go a little bit farther into the future, right? If you now know how to predict t+1, you know, this resembles the maths proof of, say, by induction, you can keep doing this, right? An indefinite amount of times in the future. Okay, so I'll touch upon 3 ways to forecast, and so the first, so these are the 3 most popular ways of forecasting, 3 state-of-the-art, say 3 which represent the modern ways of doing sequence forecasting, right? We'll see to which of these provide state-of-the-art performance. So we got RNN and LSTM. We got temporal convolutional networks, which is TCN, and then we got transformers, which I've abbreviated with TF. So now, recurrent neural networks. I'll try to be a bit faster on this because this doesn't provide state-of-the-art performance. And so I think I would rather spend my time on things that actually work better. The RNN is easy. So you've got a single module that you repeat n times. You got an internal state. You use the internal state to predict the next internal state. You feed into the internal state and you predict from the internal state. So everything happens starting from this HT, and this is a modular architecture. It's as easy as it can be, and it generally works well at the first try. So there's very little tweaking that you need and very little knowledge you need to have before you can actually get it to work. This is a great advantage. Of course, you need to, as you generally do with machine learning, you need to have a loss. You need to define exactly what you want to predict, right? So for example, in our case, we want to predict shear stress. And so we want to predict a certain value. And we use the L2 loss, meaning we want to minimize the Euclidean distance between the value that we predict and the true value that was observed in the sequence. Well, during training, you need to observe sequences, and you need to predict sequences into the future, and say the RNN are cumbersome at training because they need to go step into step into this computation and update of the internal state, and so they need to have this unrolling during training, so which does not allow us to say to parallelize the training, right? So you need to go through a for loop where you backpropagate all of your gradients. This is a bad thing. Also, because of the fact that you need to say go through this internal state at all times. So this is some sort of checkpoint you need to have at each instant in time. You also have problems with memory, and for this aspect, we have a solution because we got the LSTM and that is a modification on the basic RNN module. And there we have a parallel track to the one of the internal states. And this fixes some of the memory issues. So the equations get a little bit more complicated and also the structure of the model, but this partially resolves the issue of memory, because there is a sort of a shortcut in the backpropagation of gradients. Still, training does not parallelize, and still the long-term memory is not good. So it's this still is a problem. But what I've told you about still holds. So it's the positive aspect of this is that it's super easy to make to use it, and you can actually bend it to do even naive things. I mean, for example, we have applied this to trajectory forecasting, and you can take the internal state and you can actually say, you know, the internal state now represents the status of each of my agents. So I've got people, and I want to be observing people and predicting people into the future. The LSTM, there is one LSTM for each of the people, and the internal state now, I'm assuming, represents each of these people. And I can combine this to have some social term. So we know that people move on the ground depending on the influence from others. And this internal state in the LSTM actually gives us the way to deal with that in a very easy way. And so we have used that, not only, but we have also modulated this and according to what the people actually can look at. So, you know, people have got their head, we can estimate what they look at. And of course, they are more influenced by people that they can see rather than people on their back, which they cannot see. And including the visual attention for people and including the social term actually allows us to have better prediction. So this works effectively. Right, it's actually here we're predicting some Gaussian distributions, in fact, not just the XY positions. We can even estimate some sort of uncertainty, whereby we assume the uncertainty is given by the variance of the Gaussian distributions. I mean, any questions so far? Any doubts or okay. Okay, then I'll get into what is a second way we can do, a second way how we can actually do forecasting, and this is by using 1D convolutions. Now you see a very simple video here that that has got a small kernel, which is this thing with sliding over our input. You can imagine that this is time, and you can imagine that this is our shear stress, so to say, in the past. And at each point in time, we want to predict, for example, at some future horizon, we want to predict the shear stress, right? And of course, this is just a very simple example. This is a one layer CNN, one layer, one-dimensional convolutional neural network. Because we apply that to time, we call it temporal convolutional network, so TCN. But it's nothing more than this in its basic concept. And And of course, the kernel of my convolution is what I'm going to be learning. This kernel is what learns how to manipulate the past in order to provide the future. Right, this is another way to represent it. So you can consider that you have a sequence. It can be a sequence of words, of course, and the convolution takes some of this sequence embeddings and it processes that. What we need to make sure, but this is just a very small detail, is that this is causal, meaning that we always only consider things that are happening in the past. And so for this reason, generally, when we talk about TCNs, we generally represent it this way. So we have observations 0 to t, and then based on those, we predict t plus 1. And so you can assume that this is a sequence of shear stress values, and we're predicting at t plus 1 the shear stress. Now, of course, you can then take this one here and put that into the input to have an autoregressive prediction. Now, this is super simple. And this is also actually parallelizable, which means that differently from LSTMs, this actually can train much faster. The kernel uses the temporal dependencies, so the kernel can actually look at what comes one step before and one step before the one before, so 2 steps before. But what we can get into when we consider this sort of, say, convolutional neural network is that, you know, imagine that, imagine this simple example, right? Here I've got 2 layers. And if my kernel, if my convolutional kernels are 3, then I'm gonna be, for, say, in order to cover a sequence of 5, I need 2 layers, right? So in order to cover a sequence of, say, 7, I need 3 layers. There is a linear dependency between the length of my sequence and the depth of a neural network. And here the problem is that deeper networks are more difficult to train, and they also have more parameters, right? And there's and the sequences that we want to deal with are about hundreds, at least, of values of the shear stress in the past, which means we're going to have hundreds of layers if we use this simple procedure. So actually, what is really the small, say, addition of complication of this temporal convolutional network is that we have a dilation that doubles at each of the layers. Dilation means initially the kernels are covering, say, adjacent steps in time. And then the more we get into the network, the more we go up the layers, the more they actually leave a gap. Doubling this assures that we actually see all of the inputs. That's what we want to do. So we could, of course, avoid this and just neglect some of the input. But this may mean that we actually don't see it, some of the input, right? So the reason why we have this procedure is because we want to have every output be aware of any of the inputs, also for long-term inputs. If we do this, the relation becomes logarithmic. Therefore, more manageable also for very long sequences. All right, so, and then I get to the transformers, which is the, say, third modern way of doing sequence modeling and so forecasting. And this is the basic transformer network. This was proposed in 2017 by Vasvani et al. And it's based on attention. And it's an encoder-decoder architecture. So I'll get back to this when I switch talking to graph convolutional networks. So encoder-decoder means I've got my input here. So this is here, what I see is I've got x minus 7 up until x0. So I've got 8 observations here. And this is what really I've observed. Based on this, I encode a memory of anything that I've seen so far. And this ones I see on the right are effectively my predictions. I start predicting shear stress at time 1, and then I predict at time 2. I put it back into the input and I keep predicting. But effectively what happens here, which is different from all the others, is that I'm not going to touch my memory. My memory only refers to what I really observed. And then anything else that is predictive autoregressively, yeah, is not going to affect my memory. So this is kind of a, you know, a pictorial video for that. So you got all of your input, and your input basically gives you the encoding, and this is your memory. And then you predict, and this is a pictorial, say, demo of the prediction. The prediction proceeds in an autoregressive way. So meaning that you start predicting with a, say, start of sequence, give me the first one, and then you keep predicting, give me the second, the third, and anytime you put your prediction back into the input. But the memory stays constant, say untouched. The basic equation of the transformers is this one that tells you that in order to predict, you basically consider each element and you compare each element with all of the others. And based on this comparison, you weight the combination of all the others. Of course, this picture is actually wrong because this is just a basic transformer. But the time we start applying this to shear stress, you will only see this sort of attention towards the past, right? In the encoder, you can see future and past because in the encoder looks at the observed sequence. And so it's effectively like this. In the decoder, you have a sort of causal attention. So you only see and have attention towards anything that happens in the past. Now, this is also easy to parallelize. And the great thing about this is that the path length between any point into the future and any point into the past is actually constant. You don't need to have any unrolling like you had in the RNN. So this unrolling is problematic because you need to be able to manipulate memory, decide anytime what you want to memorize and what you want to forget. right? And here you have a direct comparison. Putting this into comparison and in terms of performance is also a little bit unfair because the transformer effectively has got attention to all of the past. So it has got potentially an unlimited memory, while in the RNN, you only limit your memory to the internal state. Right, so I put it here. So it's in terms of complexity for the current numbers, dimensions we use, and length of sequences of hundreds, they're comparable. There's no difference in complexity between this. The big difference is in training, because the transformers and the TCN can be parallelized. And the big difference is in the path length, because the transformers can attend with a constant complexity to any of the inputs or previous predictions, while the RNN, I've got an issue with that. We have used this just to say for people prediction. This is not say potentially of interest to you, but just so to say this is providing state-of-the-art performance and also multimodal futures. So people move potentially into plausible multiple futures, right? This may also happen to the shear stress, and the transformers are good for that. So just to say, summarize why we believe transformers are good. These are the state-of-the-arts in NLP, maybe by now also in computer vision, and they transfer incredibly well across domains, which means potentially if you train on shear stress in one area of the world, what you find and what you learn applies to another one area, which is very different from the one you trained on, right? So transformers have also been used to transfer from audio to video, which are quite different. But they're complex. So, and most likely the first train will not succeed, will diverge, because there are many knobs that need to be turned in order to actually get an understanding of that. And second complication, there is a sort of a, a threshold. If you don't get to have enough data, you won't get any performance at all. And this is a big problem, of course. And in fact, it started to be successful only, say, after reaching a certain amount of training data. All right, so let me see. Okay, so well, just I'm going to be now showing some experiments with the shear stress. We're predicting the shear stress. So we're going to be observing this amount of shear stress. This is 20 seconds, and this is 200 steps in terms of, say, without sample depth. And so this makes 200 steps in time, and we want to predict 100 steps into the future, which means 10 seconds. Where you see the star in this illustration, it means we stop here and we start predicting. And so you will have basically your output that you need to compare to the ground truth. So we predict orange, but we should have predicted green, which is what happened really in our recordings. This is a train, validation, and test split. When we do machine learning, we want to separate what we train on and then what we validate or test on. And The reason for this is that deep neural networks are extremely good at memorizing. So they can overfit very easily. And if they overfit, they will just memorize, and then they can reconstruct your training set without troubles. But this is not the purpose of that, right? Because you learn on some patterns, and you want to be able to predict in the future, for example, right? Things that you have not seen. You want to learn from anything that has occurred so far to be able to say that in a month from now, there will be a small earthquake here, right? All right, so what do we observe? When the signal is periodic, there's no difference between the LSTM, the TCN, or the transformed, or the transformer. They all do well. And this is also happening in terms of numbers. So we measure the R-square, but we also measure the root mean square error. And so for the root mean square error, the lower the better. For the R-square, the higher the better. So the perfect score is 1. For the root mean square error, the perfect score is 0 error. There is very little variability. Also, depending on where you start predicting. So you can start predicting here or here. So on the ascending part, where the shear stress is loading, or say potentially being released. So this doesn't affect the performance so much. The case of the semi-periodic signals, in the case of the glass beads, is definitely more troublesome. And this is most troublesome for the LSTM. But I would say none of the models really go that well in this case. The temporal convolutional network do the best. What we have observed is that in this particular case of the glass beads, what we're really suffering from is this sort of irregularity that happens around the peaks. The fact that there is this sort of, shape here. So the black is the ground truth. You see what happens. And somehow our model is struggling to understand that after this small pattern, actually the shear stress keeps loading and then it will release only afterwards, right? So this still work that we need to do. And then there is the case of slow and fast, which where basically we see that transformers and TCN are doing well, but the LSTM is suffering. Here, I want to explain why we have here pre-train, right? So here, this is the transformer that we have pre-trained on synthetic pre-training data. What this means is that performance was not that good if we didn't pre-train the transformer, because the transformer needs a minimum amount of data. And so, in fact, you see that there's a big difference between pre-training or not pre-training. So what's the meaning of pre-training? Well, we had a data set, and we just generated synthetically a number of very simple sine and cosine patterns. But by using this, we pre-trained on a data set which was 100 times larger, just sines and cosines. And then we moved to the actual training set. So we pre-trained on 100 times larger training set, and then we fine-tuned, say, on the actual shear stress sequences. And you see that in numbers also. So pre-training makes a big difference. In in the positive cases and also in the negative case. Right, so some final remarks on this first part, right? So the LSTM are flexible, but they're not state of the art. The TCN are simple, and they are the preferable models for modest data sets. The transformers are probably the future. We're going to have larger and larger data sets, and there we can see that this really shine. What I believe is important in this study is to think about forecasting in autoregressive terms. So you teach your model to predict at time plus 1, and you keep predicting by always considering what you've just predicted. And what is also important, what I would like you to take as a take-home message out of this is autoregressive has got a very good influence on performance, but also it's important to think about forecasting models in earthquakes in terms of self-supervision. Because if you are predicting your entire signal, you don't have the ambiguity of labeling. And you also avoid what is known as supervision collapse. So just predicting one label instead of predicting the entire signal. Right, and potentially if you keep doing this and combine these two, you can predict at an indefinite time in the future. All right, this concludes this first part. And so I don't have much time left actually. But I would like to get into the second part and at least show a primer on graph neural networks. But before that, I'm open to questions. Then Chris will tell me how much time I have left.
I have a question, Fabio. Excuse me, Chris. Fabio, have you used synthetic data to train on for the future prediction of person's movement, or how do you deal with that problem?
That's a good question. So it's in the case of movement of people, we didn't, because it turned out the data was already enough. So we had robots. We could just keep recording and have more data for
so
that.
You had a massive training data set.
Yeah.
In the case of the laboratory data, you pre-trained on sines and cosines. What if you had trained on, for example, using rate state friction or some other frictional law? Do you think you would do better, worse, or the same? Do you have any insight into that?
Right. So if I understand the question correctly, is change the friction during the experiment, right? That's what you're asking.
Let me be clearer. So if you generated many synthetic data using some friction law, it could be rate state friction, it could be any frictional law, to try to reproduce or produce behavior of slow slip, stick slip, etc., rather than training on simply sines and cosines. Because the problem with the sines and cosines, it's only going to work for periodic data, as far as I can tell. But you could have aperiodic data if you simulated using some sort of frictional law. By doing what you're suggesting, you could change the friction, for example, during simulations. So you could have many different frictions that could evolve in time, etc. what have you thought of doing that? And what if you have thought of that? What are your thoughts in terms of application to this problem?
Right, we haven't done it, but I think I would expect this works much better than sine and cosine. So exploiting effectively your knowledge of the physical system, if I understand it correctly, would yield a much more abiding, say, set of training set. And of course, the closer the training set to what you want to really predict, the better the output. Yes, absolutely. And for example, this happens all the time. Currently, for example, for autonomous driving or robot unmanned vehicle moving around, for example, deliveries by Amazon Scout. What Google, Amazon, Facebook are trying to do is they trying to get their own digital world. So they're trying to synthesize by computer graphics everything into the future. Something that you cannot simulate is, for example, a car running onto a pedestrian, right? That's what you want never to happen. And so, but you need to simulate that. And simulating turns out to be a very good thing for, say, generating your training set. The better you can simulate, the better the model also then transferring to real data. Absolutely. So yes, way to go.
Great, thank you very much, Fabio.
Mm-hmm.
Let's add to that, Fabio, this interesting question about pre-training. I guess the problem would be that if you want it to be self-supervised in any way, then the pre-training is tricky. You have to decide how to pre-train. You know, what Paul's suggesting could certainly work, but it seems like you might end up putting the answer in, because you can take a friction law that's complicated enough to produce period doubling and some of the other things that are seen in the experiments, and then how do you decide, like, at what level do you decide to stop for pre-training, Fabio?
Right, that's a great observation, and this was also my some sort of say. So we recently had a visitor, so some sort of you know, one of the most influential computer vision scientists, and what we effectively do is we actually do it. We simulate a lot of say graphics in terms of imaging. And then we train our models on simulated data. So currently, I see what you mean. So if we can simulate it, we know the answer. So why are we doing this with the neural networks? So I mean, effectively, the neural network would learn then this thing that we know already, right? Or at least to say, if I can synthesize a computer graphics world so well that it resembles the real world, I also know the answer on how to use it to say whether somebody is going to jump onto the road and I need to brake the car, right? Effectively, maybe this is a limitation of the models today. We're not able to invert prediction models. So we prefer to synthesize photorealistically as well as we can, and still train our models to predict. So with a predictive goal, it's a limitation. I think it's what works best today, not necessarily what we need to do for the future. I think it's a great point.
Yeah, great, thank you, Brendan. Thank you, please.
Mm-hmm.
Thanks, Fabio. Thanks, Chris. In NLP, transformers have seen obviously tremendous success. And a lot of that is sometimes attributed to the highly tokenized or highly quantized nature of that problem. In the time series problem that you're addressing, are you treating the time series as continuous, or are there kind of quantization levels that you could do there to make it more like the classical NLP problem?
Right. So I can offer you an answer which is not within the the earthquake domain, but it has got to do with people motion forecasting, because there we've done this experiment. So it turns out so currently what you have seen is a continuous problem. So we're predicting the continuous value of the shear stress. So it's a what we call a regression problem. So we're regressing an actual continuous value, and then we compare it with the L2 loss towards the ground truth. But of course you can quantize it, and if you quantize it, you predict not anymore a continuous value, but you classify, basically, right? So you have a classification problem, and you can quantize, you can choose your quantization, right? You can quantize into 1,000 way, so 1,000 classes, so that you have a small error. What we have observed is that effectively regression is very close to quantization. The more the quantization is better, the more the classes, the better the quantization, but you pay for that, because effectively, when you add more classes, you effectively have a more complex model and more parameters as well, because it's a 1,000-way classification, and you need to have parameters for predicting into any of the classes. Right. So it's a good question, and but honestly, so I think the answer is regression is not that far from the quantified. Actually, to be honest, maybe if you want, and sorry, I'm kind of deviating from this. I'm saying performances are similar, but what the reason why I like quantization is because it allows me to make multi-model future prediction. So the moment you're predicting classes, there's no limitation in saying I'm predicting class move right, but I'm also predicting a class move left, right? When you regress a value, you can't say that. So regression would end up in the middle, while if I'm predicting and then I've got quantization into right, middle, right, straight, left, then you can also say I'm at a T junction, and then I can go right or left, and I can predict those two, and I can keep predicting two likely futures. So actually, that's why I really think that quantization is, in some sense, the way forward. Thank you.
Hi, Professor.
Hi.
Yeah, I would have a question on how you do the pre-training and fine-tuning. So you pre-train all the transformer with the synthetic sinusoidal waves. Then after that, if you fine-tune the entire model with smaller learning rate, is that the case, or you fix some part of the model that you don't change?
Okay, so yes, so basically you initialize from random parameters, like you basically do say training from scratch, right?
Mm-hmm.
With this, we have a million tracklets, so it's million sequences that we train on. After that, I'm not entirely sure, but I don't want to say something wrong. I don't know if Laura is connected today. Maybe she can, maybe not. But so when we fine tune, we don't have. She's connected, so she's been dealing with this fine tuning, and I think she can tell you about the learning rate. I think there's no freezing into any of the parts. The learning rate, she can probably tell you more. Laura?
Yeah, I'm just checking, but the learning rate is similar, the same in pre-training and fine-tuning.
So in a nutshell, there's no, so it's not we just do it like we keep training, but then at some point we continue training on the actual sequences.
Okay, okay, got it. So the in the pre-training and the later fine-tuning, the learning rate are the same. Is that the? Oh.
Yeah, and yes, I think so. I think Laura is pointing to the answer that yes, they are the same. What I also don't remember whether we restart the training in terms also of warm up. Laura, I don't want to put you on the spotlight. Maybe this is a very good follow-up. She can tell you more about this.
Yeah, we just continue the training, starting from the pre-trained model and then fine-tuning with the actual sequence of laboratory earthquake.
Okay.
Mm-hmm.
Okay, thank you.
Thanks.
Other questions right now? Because otherwise, maybe we let.
Ask you a question.
Please.
Thank you so much for the talk. And I have a question regarding the if you try to use different sequences as input for training, and so changing the temporal length of the input. And also, if you have investigated the attention scores within the sequence that you have used as input in the transformer, of course.
Right. So, I mean, also here, I mean, Laura, feel free to jump in. I think we didn't experiment on different lengths. We have considered this fixed length, say, of 20 seconds and predicting to the future for 10 seconds. And no, we haven't considered, I mean, Laura, feel free to just jump in if you like, but I think we haven't done a study on attention. I do have a number of say studies regarding motion of people where we looked into the attention, and actually in this second part of the talk I've got a picture of that. It's not always easy to understand though, because it's a sequence, it's a temporal pattern, so it's not really straightforward to decode what the attention focuses on. And also attention is something that changes layer wise, right? Probably the one attention you can decode more easily is the one at the lowest layer, layer 1. But as soon as you go higher in the layers, attention is, so take it as very, say, rough terms, it's really not intelligible, not that easy.
Okay, thank you so much.
You're welcome.
Other questions right now? And maybe we let Fabio, continue, and then we have some additional time for questions.
Chris, more or less, how long do you think I can take just to modulate?
I don't know. You're asking me for a prediction. I don't have any pre-training data for this particular prediction, but we typically try to end by 1800. So okay, so maybe talk for half that time and questions for half. Does that seem reasonable?
Yeah. Okay, I'll do that then. I'll just pick over on the way. Mm-hmm. Okay, so this second part is about something that I'm really excited about. So it's graph neural networks, and so in this part is into, so we haven't applied this to earthquakes, not yet, but we had some work on motion prediction, and this is state of the art, and also incredibly fast, especially because of this. It's not deep, right? So So let me start with the primer on graph neural networks. Now, the thing you've seen here is a one-dimensional signal, right? And we can consider a plane as a grid where people are moving through, and this is also then a two-dimensional problem. But in many cases, we don't have grid, right? So, for example, in the case of a person moving, where you actually have joints, you don't have a grid, right? It's if you project into the plane, it's not Euclidean, and that's so in general, say you can imagine that the situation on the right also may occur, for example, right? So just to mimic why you may want to use it in earthquakes, you can assume that maybe this is each of this is a station that records some signal, right? And so you want these stations to exchange information so that you can actually reach a better prediction. So far, we have dealt with just one single station, say observing one single signal and predicting. But we can do much better if we actually can leverage more of this. And of course, there's graphs are flexible, very flexible. You may have graphs where you don't necessarily have the node ordering. You have node ordering with the body parts, because you know that the head is the head and the right arm is the right arm. But otherwise, here you can't say this is right or this is left, right? It's just you have neighbors. And the graphs and the theory that we've been developing over graphs can take into account also dynamic graphs. So imagine that some of the stations may slip some meters away because of an earthquake. You still want to use all the previous data that you had, right? Okay, so what mainly changes here is the encoder of your past. This is what turns out to be the best structure for forecasting, is that you have an encoder, which is a graph convolutional network. Let me just be a little bit more clear on this. So this is a graph convolutional network GCN encoder, which takes a graph, has got multiple layers. There is a nonlinear activation like you have with the deep neural networks. And then afterwards, you have some knowledge of everything that you have observed. So that's something that here on this arrow that you can make prediction based on. This is similar to what you observed, for example, for the case of transformers. So you observe your past and you encode this into memory, which you use afterwards to predict into the future. So you have the encoder and the decoder, and the decoder is the one that starts predicting and keeps predicting autoregressively, right? Now, in the case of GCN, in the case of graphs, you effectively need most of your, say, machinery here into the encoding to understand the potentially non-Euclidean relation between the observations you have at the nodes. And then you predict with the simplest model. We said that the simplest model is the TCN. Well, the TCN suffices for state-of-the-art performance. So once you have an encoded signal here, then TCN gives you a good prediction into the future. So what I'm going to be focusing on is not on this, because this is extremely simple. This is just the 4 layers of a TCN, nothing more. But this is the complex, the part that can get complex. Given the time, I wouldn't want to make it too mathematical. So, but you can imagine that a graph is something where a graph is defined by a set of vertices, V. It is defined by the relation between these vertices, which is encoded into a matrix that we call an adjacency matrix. And in this adjacency matrix, you basically have the pairwise relations between the vertices. You have your features at each of the nodes. So you can imagine that each of these nodes is a station where you record your acoustic signal, right? And or you can imagine that this feature comes from the XYZ coordinates of a human joint. You can do graphs for a number of applications. So social networks, user profiles and user images, biological networks, because molecules are graphs, or human motion, like we have applied. And so here the nodes are the body joints. The big difference between the CNN, the classical CNN that have been so successful for images and the graphs, is that in the CNN, you know this is right, you know this is left, you know this is top, bottom, top right, bottom right, and so on. And you can encode specific kernels for this. But when you're in a graph, you can't say what is right or left. And so you want to have a general procedure to do exactly what you do here. In the end, what you do here is message passing. So you compute the value that you got in this pixel based on message passing from whatever it sees. This is the receptive field of a CNN. And in the graph, you want to have some sort of aggregation function that gathers the messages and processes them. We need to determine the graph, and then afterwards we need to learn from the graph. And say theory on graph convolutional networks have devised procedures for both of them. The key idea here is that we want to generate some node embeddings. So each node, each joint of the human body, we want to encode. Embedding means we want to understand it. We want to develop some feature vector that characterizes it based on its neighbors, based on the local neighbors, right? And so we effectively gather information from neighbors. So A and C give us information on the node embedding of B. But then this message that is now of B, we can gather together with C and D to actually make a local neighborhood and message passed to encode the local neighborhood of A. Now, where are the neural networks? Well, these are in the aggregation of the messages that are coming from the neighbors. And the neighbors define the computation graph. So defining the neighbors of a node means defining the graph, and that's also how you do the forward, so passing the messages, and then back propagation. Now, something key in the graphs is the depth. So the deeper the graph, the larger the neighborhood. So if you consider node A, then at layer 0, it's just A. At layer 1, it's the one hop neighbors of A. So it's D, C, and B. And with one more layer, you can gather information from nodes that are one hop farther away from A. So if you consider 2 layers, then you also have information from F and E, which are both of them 2 hops away from A. And that's what you see basically here, right? So with 1 layer GCN, you only gather information from the direct neighbors, and then you can actually gather information from those that are actually two nodes away. Now the key to the graph neural networks is actually how you do the aggregation of the neighbors. And so basically, what's in the box? Well, the basic approach, which also turns out to be one of the most effective, is that the messages you can average, the simplest thing. And then afterwards, you apply a neural network. So keep this in mind, because this is exactly what we're going to be looking at in this complex equation. So this is nothing but exactly this. So we average all messages, and then we apply a neural network. So we have an input, and then we propagate this layer-wise. Let me just skip some of the parts. So this is your averaging, and then the W is your neural network. And then there is a nonlinearity, because every neural network requires that you have a nonlinearity, otherwise you don't have layers. You just have something that can be written as a one layer. Now, we want to get to one very easy equation, and it turns out to the average a neural network that we've written before as a summation can actually be written down in a matrix form. And if we write it in the matrix form, then this turns out to be D is the degree matrix. And then you've got the inverse of D, which is still a diagonal matrix. A is the adjacency, and H is the embedding at a certain layer, L. So really, the graph convolutional network is something that is extremely easy to write down. This is the equation for each layer of a graph convolutional network. So here you've got your embedding. W specifies the transformation that your neural network does, and A is your adjacency. So this is encoding how each node is connected to other nodes. So it's a simple formula that you need to repeat. And right, so at this point, I see where we are in time. So I would just tell you very briefly that we can apply this to key points. And this has got some novelty in what we devised. We presented this at the top computer vision conference in June 2001. And we actually got performances, and I just want to show you what really is the reason why I think we should consider this rather than potentially transformers to some extent. And the reason is because we actually get a huge increase in performance. This is an error, and we reduce it by 34%. But also, this is an approach which is based on RNNs, and transformers do not make it easier. And this requires 3.4 million parameters, while actually if we do it with non-deep graph convolutional networks, the number of parameters is just 57,000. So it's a huge save. And this means we can actually also train with less data because we got less parameters to train. And this applies also to other data sets. So this is just other data sets. And you see how we're predicting the human motion. So this green and magenta is what we're predicting after the blue and gray. And yes, so we can have a look into the sort of attention, but it's not that easy to encode. But I think in the publication we give some information. I think this is quite difficult to interpret, to be honest. Right, so I conclude here, and sorry for the rush, for the final rush. I hope I got the main message through.
Wonderful. I'll ask everyone to please unmute. Yeah, long enough to let's join and thank Fabio for a fabulous talk.